in this session, we will see the Lasso and Ridge regression, how we can implement it by using Scikit-Learn library. So in the last session, we have seen in more detail and in more visual representation how Lasso's objective function, or you can say cost function, works. How penalty L1 penalty, when we add to the cost function, it decrease or shrink our coefficient that we already have, or it can also eliminate coefficients by making them zero. We also have seen ridge regularization. In the case of ridge regularization, we have seen that, like here you can see again, in the ridge regularization, when we add L2 penalty in the cost function, then our parameter values are you can say shrink, but ridge regularization cannot make them equal to zero. Okay, so today we will see how we can implement them by scalar. So before that, in the end of last session, I told that we have implemented till now linear regression. When we have used the linear regression for single variable, an example of linear regression, multiple regression, polynomial regression, till we are using linear regression class. Okay, in which I told you that linear regression class implemented by sklearn use closed form solution. Okay, we have learned two type of algorithms or two type of concepts how we can train the linear regression model, or how we can get our optimal parameters. One we have learned closed form solution, and second one is was a gradient descent. And I told you the lasso regression provided by sklearn, we implemented the algorithm by using gradient descent. Okay, regression by sklearn trained by using gradient descent, and ridge regularization has both options. Okay, so before that, uh, it is important to tell you that there is no restriction that just these two algorithms like closed form and gradient descent. Just these are two algorithms to solve or to get parameters. Okay, these are the general two algorithms. Like in gradient descent, there are some variations in gradient descent, like batch gradient descent, mini batch gradient descent, stochastic gradient descent. That we have learned was a batch gradient descent. So there are multiple variations in the gradient descent, and also when in the case of closed form solution, there are also some variation in the computation. Okay, sometimes some core mathematical terms used, like a singular value decomposition, SVD used. Okay, but these are not uh, like important to go in the detail of them. But before that, here why I am telling you about that, because sklearn implemented them. Okay, there are multiple solvers in the Ridge. We will see the documentation of Ridge provided by sklearn. So in the case of okay, so why I am telling you? Because in the case of gradient descent, if I will show you here, in the case of linear regression, we have seen the multiple here, like this one. Okay, in the case of gradient descent, you have seen that gradient works in that way. First, we have to random initialize our parameters. If I will zoom in, random initialize our parameter values. Then we have to calculate the partial derivatives of cost function with respect to each parameter. Then we have to update our parameters in the opposite direction of gradient. And the last one is repeat step 2 and 3. Still, we reached maximum iteration or minimum cost function value achieved. What exactly this step 4 is that the process that we are repeating, taking derivative, update our parameters. Again, taking derivative, update our parameters. How many times we should run that loop? Okay, this is that how much iterations we should want to optimize or to get our optimal parameters. So this is provided as a parameter. If I will show you here, right here, in the case of lasso, in the case of lasso, you can see here there is a parameter max iter. Okay, this is a maximum number of iteration that is by default 1000 times. This lasso, in the case of lasso, when we use lasso by sklearn, 1000 times it will repeat that process of updating parameters. Okay, by default we can also control it by passing some value in that parameter max iter. Okay, okay, so now come back to what is the reason that I am explaining you here this one. The reason is that in the case of, if I will make here in the simple way, in the case of linear regression, when we were using linear regression, okay, in the case of linear regression, in the case of lasso, in the case of ridge, okay, I will make them regression. I will zoom that so you can see clearly. Okay, in the case of regression, okay. So in the case of linear regression, if I will use another pen here, in the case of linear regression, our post function was just mean square error. Let's say, okay, mean square error. In the case of linear regression, in the case of lasso, we have our post function. This one, we have our cost function in which we have added some penalty with the alpha parameter. Okay, some penalty like a L1 penalty. Let's say, okay, L1 penalty we have added in this. In the case of reach regularization, we have our cost function like this, mean square plus alpha, to control the strength of penalty, how much we should penalize our cost function or mean square error. Here we have L2 penalty. Okay, actually we have squared L2, but for now we have L2 penalty. We add in the cost function of in the case of reach regularization or in the case of regression. Okay, so if I will make here alpha equal to 0, if I will use this one, if I will make it alpha equal to 0, it will become the same as the linear regression. Okay, and this will also become same as linear regression. Okay, but when we will do practically by implement by using these libraries provided by the sklearn, provided by these classes from the sklearn, maybe we will not get same result that we are getting in the case of linear regression. And in the case of lasso regression, when we have made alpha equal to 0, okay, actually they have, when we will make alpha equal to 0, the linear regression and lasso regression should have same cost function, so they should have same type of parameters in result. But we will not have. The reason is that linear regression class by sklearn is using uh, closed form solution. Okay, lasso used gradient descent approach, and reach has both options, but again you will not exactly the same result in the case of reach. When you have made alpha equal to 0, the parameter values that you have calculated by linear regression. Okay, so they have multiple options, 1 2 3 to so on. And we will also study in the case of logistic regression when we will start our supervised uh, machine learning module in for the classification problems, where we will also see in the more detail what are the different solvers. Like we have studied gradient descent and closed form solution. We will see how some variations of closed form solution and gradient descents are available and how we can use them. Okay, so for now, without wasting time, we should move on our part of code. So okay, before the code, I want to elaborate here. In the case of linear regression, you have seen that parameters. So I will not go in the detail of that parameters that we'll have in the case of lasso. Okay, like fit intercept, we know that why we should use fit intercept, that we want intercept value or not. Okay, in this way we can use that fit intercept is equal to false, that we are wanting such a model that just have coefficients, no any intercept. Okay, Then normalize, we can use to normalize the values before feeding the data to our model for training. Then copy x to copy, and jobs is not it's for parallel processing, but in our case it's not unnecessary to learn. In the case of positive, that we are forcing our coefficients that to be positive. Okay. So these are parameters are in the case of linear regression we have learned. So when we will move on the lasso regression, there are some extra parameters. So first of all, if I will show you here what cost function it is using, there is some variation they are using. They are not using exactly mean square error like this cost function they are using, uh, and plus penalty. This is L1 penalty is the same that we have seen. Alpha that we are using here the symbol lambda. Here they are using alpha. Okay. So this is the cost function, which is not exactly the mean square error, because in the case of mean square error, this is sum of squared error. Like this is our true value. So y is true value. This is predicted value, and then it's a summation and the square of them, and divided by it should be divided by just n. Okay, that like a f if we have n number of points, but they are dividing by n into 2. Okay, there is one extra factor which is 2 in the denominator. So but really the purpose of that I don't know, but it really not matters. Okay, the parameter values which will give this minimum like a minimum cost function, uh, the same parameter will give you the minimum cost function at this also. Okay, like I told you multiple time that means if you are using mean square error, if you are using sum of squared error, your minimum will be at the same parameter values. Like in the case of ridge, if I will show you, ridge actually use sum of squared error here. Okay. But in the case of so they have some variation. I don't know exactly what is actually the reason. Okay. If we will study the code of that lasso regression, we can figure out what can be a reason why they are using 1 over 2 into n samples. Okay, instead of just 1 over n samples. Okay, they are using that one as an objective or cost function here. Okay, anyhow, moving come back on the parameters. Okay, so parameters. Okay, one another concept that I am not telling you here is the elastic net. Okay, elastic net is a variation we will study in further modules also, hopefully in the next module. Elastic net is, you can say it's a combination of L1 and L2 penalty. How much we want L1 penalty, how much we want L2 penalty. There is a variation that we can use in some algorithms, in some libraries, like if in the case of logistic regression, if I will show you here. Yeah, in the case of logistic regression, there is a variation that we can use L1 penalty, L2 penalty, and elastic net. Okay, we can tell that we are interested in the combination of both L1 and L2 penalty. Okay. Anyhow, we will not go in the detail of elastic net. It is really simple, but for now, it's just we should remain on the L1 penalty and L2 penalty. For L1, we are using lasso. For L2, we are using ridge regularization, or uh, as we are solving regression problems. So lasso regression we will use here in the case of L1 penalty, and in the case of ridge, we are using in the case of L2 penalty, we are using ridge regression. Okay, so come back here. Alpha, alpha is like we have lambda in our cost functions. Like we have here lambda. Sorry, I have also today I have mentioned in the form of uh, alpha. I have mentioned, but usually we have used the term lambda. If I will see here, mm, yeah, we have used the term lambda and here actually. Yeah, but it's really not matter the different notations, but the concept actually matters. Uh, what exactly this is representing here? Okay, this is representing how much the value of alpha will represent how much penalty we should we want in our cost function. How much penalize we should do our cost function or our mean square error, you can say in short. Okay, so this is alpha here, in which we can pass any value. If we will make alpha is equal to 0, it will be same as we have cost function for the case of linear regression. Here the fit intercept, same parameter that we have in the case of linear model, linear regression. Fit intercept normalize is the same parameter. Pre-compute it's not necessary here. Okay. So copy X, it's again the same to copy if we want to copy our data. For that two parameters, I am telling you this in the detail. I have explained that max iteration and tolerance. Okay. Now maximum iteration that I have told you in the case of gradient descent, we have we can specify how much iterations we want, uh, how many times we want to update our parameters. Okay, sometimes we don't have a restriction on the our iteration that we want as much number of times we should do, we should iterate uh, our algorithm, our parameters, until we get our uh, this you can say until we get our optimal parameters with this tolerance. Okay, like here we have a parameter, another tolerance. It works in that way. By default it is 10 raised to power minus 4, you can say 0.0001. Okay, it means if you are updating your parameters, okay, in each iteration your parameters are updated. If the updation, okay, that you have updated your parameter, the up the difference that the parameters values that you have before, now after updating you have some different parameter values. If the difference between the previous and the now is less than 0.0001, then the algorithm will stop there. Okay, if the difference is higher than 0.0001, then it will keep on iterating. Okay, tolerance is it's actually mean how much tolerance we can bear in our parameter values, which are away from our exact optimal parameters. Okay, because in when you will see in the neural network, we will do in the detail graded descent how, because sometimes when we are iterating our well, let's say I can tell you here. Let's say we have this cost function and we are iterating in this way. Uh, Sometimes we are iterating in this way, like in this way we are iterating. Okay, and this is our exact uh, minimum of function. Okay, minimum cost function or minimum, at this point our function is minimum. But sometimes when we are iterating, we jump on this side. Okay, and when we see that our cost function is our error is increased, then we to decrease that, when we move we will again jump our optimal parameters. Okay, so to control that, there is another parameter that we have learned in the graded descent, learning rate. Okay, we can decrease the learning rate here. If in the start is higher, then we can decrease our learning rate. But anyhow, we cannot ideally, we can reach at this position. Okay, we cannot ideally, we should bear some sort of tolerance. In the case of closed form solution, we get exact result, but in the case of gradient descent, when we have very complex functions, we should have some tolerance. Okay, here we can say mention our tolerance by ourselves, and by default it is 10 raised to power minus 4. Warm start, it's again not important to discuss here. Positive is the same that in the linear regression. Random state, again, for now, it's um, no need to discuss that random state and selection. Okay, for now, you can see it is in the lasso by Scikit-Learn using gradient descent approach. For that, the two parameters extra that we have here seen, max iteration and tolerance. Okay. Now move on the code, and here we have our code. Okay. So first, okay, this one lesson. So I am using the same polynomial model. If I will zoom in here. Okay, the code that we have implemented in the polynomial session, with polynomial modeling when we were doing, uh, the same code I will implement here. Okay, same function, this same function I will use. Just in the case of linear regression, here I will replace this linear regression by lasso. Okay, and one another change I will made here is that I will fix my degree is equal to 200, that I will artificially making my model complex. Okay, or overfitted model I am making here. I am making degree is equal to 200, and you can see in the case of degree equal to 200 what actually the result. Okay, yeah, this is our polynomial models with transformation. This is our polynomial model which is using linear regression. This is polynomial model with transformation using linear regression. In that case, when you will pass the degree 200, it is giving you this overfitted model. You are seeing that very complex on the very you can say it is getting all the variations of training data points, but very weird behavior on the test data points. Okay, here you can see. And in the case of accuracy, you can see 98% accuracy giving on the training data points and very low on the score or on the test data set it is giving. Okay, so this model, exactly this model I will use with the 200 degree. I will fix in that case, in the case of lasso. Yeah. In the case of like here I have mentioned, in here I will fix degrees equal to 200, and I will made a function. Yeah, this one. Lasso regression, I will made this function. Okay. This function, the same exact that function, just two changes I have made it here. Okay. The same function I am using it. First change is that I have fixed here the degree is equal to 200. Second change is I am using here instead of linear regression, I am using here lasso that I have imported from the Scikit-Learn. Okay, third, you can say instead of passing that previously that we are passing our degree, how much degree we want, here I am passing lambda value. Okay, how much penalty I want in my model. Okay, in my cost function, how much penalty I want. This lambda will directly move, this value will directly pass as a to the parameter alpha in the case of lasso. Okay, if I'm zoom, you can see here this lambda will go here in the alpha. Okay, now I can use this function. Okay, this function that I have made some changes in the function of polynomial. This function I will use and I will see how lasso regression works. Okay, okay. So one and other important here. If I will show you here the lasso documentation. In the documentation, there are some attributes. One important attribute is this one, sparse coefficient. What exactly means sparse coefficient? Like I told you, in the case of lasso regression, we can, when we have added lasso L1 penalty in our cost function, it can make some coefficients equal to 0 for the less important features. Okay, or you can say it can make the coefficients 0 for the features or make the coefficients equal to 0 that are lower, lesser in magnitude, or that have lesser value as compared to other coefficients. Okay, or in short, we in conceptual we usually say that it make the coefficient 0 for the less important features. But here, okay, here I am again with the coefficients. I am also printing sparse coefficient. Sparse coefficient will print all the coefficients that are not lasso has made equal to 0. Okay, that are same as the that are remained non-zero, and the if I will print the all the coefficients, then it will print the 0 and non-zero both. Okay, now I will run that. Before that, uh, uh, okay, so I will run this one, this function, and here I will show you in the case of polynomial model with transformation. If I run again this, we have this model when we have not added any penalty. This model, which is very complex model, you can see here, and very weird on the test data points. That's why we can say it is here resulting a overfitting problem. First of all, I will run lasso regression with the 0 you can say my alpha value, or you can say lambda value. Okay, that I am not adding any penalty to my cost function. And when I will run here, it will give me this function, this model. Now you can say that as we have made it our penalty equal to we have made removed our penalty by making alpha equal to 0, but it is not giving the same model as we are getting in the case of this linear regression, this class. As I told, the reason is that it is Lasso is using here graded descent approach. Okay, and by default Lasso is running 1000 times. Here it is running 1000 times. So if I will make here max iteration, max underscore iteration, if I will make it 1 lakh, let's say. So now this one, yeah. Now you will see it will give you some complex, okay, as before, like it. Now you are getting this smoother, even in the case of 200-degree polynomial. But when I will run that, okay, it is slow, but because I have increased the iterations. Previously was 10,000 by default, and now I have made 1 lakh. Okay, 1 lakh times the parameters are updated. Okay, here you can see our model is become little bit complex. Okay, now I have to again repeat I have to increase my iterations, and I can, by increasing the iterations, by decreasing the tolerance, I can get the same model that I have in that case. Anyhow, the aim is here to get the concept how lasso works. Okay, when we will make here you can see there are all the coefficients values are non-zero values, and sparse coefficient is also printing all the values here, all the 200 coefficients here. Here you can see all the coefficients are non-zero. But when I will make, and here you can see, in the case of 0, we have 92% score on the training data set, but very, very less score we have in the form of negative on the uh, test data points. In the case of mean square error, you can see mean square error on the test data set is 10 raised to power 21, which is very high, very, very high. Okay, now here, if I will run another function like, okay, 0.2. Now I am passing here the alpha value as 0.2, means I am adding 0.2 penalty in my cost function. Now I will see that most of the coefficients it will make equal to 0, Lasso regression. And it will generalize my model and decrease the overfitting. We will see here. Now, from these coefficients, you have seen that a lot of become equal to 0. I have printed a sparse coefficients. From the sparse coefficient, you can see the coefficients that are non-zero. Here total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Out of 200 coefficients, 200 coefficients, due to L1 penalty, 187 coefficients become equal to 0. Now we have just 13 coefficients. Now, in the case of 13 coefficients, we have seen here that more importantly, you can see here in the case of training data points, we have now 90% accuracy, and here 0.9 accuracy, and in the on the test data points, we also have 0.89. Okay, now you have seen how our score is increased by penalize our complex model. Okay, here you can see your model is also uh, giving you a representing good on the test data points also. Okay, now you got a point how lasso actually makes the coefficients equal to 0. Okay, now practically you have seen that by implementing by using sklearn you can do that. Now here keep in mind we are using polynomial regression 200-degree. Okay, our actually independent variable is just one, which was in our case like it was weight. if I will show you here, we were having weight our, okay, we were having weight our independent variable. We have just one independent variable. We have increased our independent variable to polynomial features, like we increase by uh, making degree equal to 200. We will have 200 polynomial features here. Okay, so here we are making it, now here it is important, and we can make our model simple, and we can avoid overfitting by making some coefficients equal to 0. Okay. Now, in some cases, lasso cannot work good where we have not, or we don't need to make coefficients equal to 0. But in our case, in this case, it is giving us a good result. And because here we have need to make some coefficients equal to 0, because we have a lot of coefficients and we have made artificially a lot of complex model. Okay, here in the case of lasso. Now, when we will see the ridge part, ridge regression by SQL, you will see that it will not give us a good result. It will not avoid overfitting. Instead, it will lead into the underfitting case. And the reason is that it will, here we have need to make some coefficients equal to 0. But ridge cannot make coefficients equal to 0. Instead, it tries to make equal to 0, but instead it will decrease coefficients approaches to 0, but not exactly make coefficients 0. And you have seen by by this graph also. Yeah, by this graph also, this lasso, when you have added lasso penalty in your cost function, it increase, here you can see it can decrease, it can make some coefficient, like here it has made theta 2 equal to 0 when it is minimizing, but in the case of ridge it is not making some coefficient 0, but it make actually approaches to 0. Like if you will see here, your theta 2 is not exactly, this is if I will show you here, yeah, this is your theta 2, it is not equal to 0 here in the case of ridge. But in the case of lasso, when you have added the lasso penalty here, your theta 2 here is on the, yeah, theta 2. Your theta 2 is 0 in that case. Okay, lasso can make coefficients equal to 0, but ridge cannot make. Anyway, it decrease that distance. It will try to minimize that is approaches to 0, but not exactly and make equal to 0 some coefficients. Okay, we will see that practically also by scalar. Okay, before going to the towards that, again, I will show you the documentation of ridge regularization. In the ridge regularization, you can see here, it is using sum of squared error plus alpha into L2 penalty, squared L2 penalty. Now again, alpha parameter to control the penalty, fit intercept, normalize, almost all the parameters. And as I told you, ridge regularization, in the case of ridge, we have multiple options. We can use multiple solvers, like Klasky solver is if we are interested into closed form solution of our cost function. If we are interested into use a gradient descent, then we can use stochastic average gradient. This one we can use, and we can also use SAGA. Okay, both SAG and SAGA we can use for gradient descent. Okay, there is another reason for that why in the case of lasso we cannot use a multiple uh, cost function or multiple solvers. The reason can be here that in the case of lasso we have function, the penalty function that we have, it is using absolute function. Okay, we are taking like a in the case of lasso, if I will show you here, yeah, in the case of lasso we have this as a penalty, and in this we are using absolute values. We are using absolute values. So absolute function is involved in the our cost function. In our overall cost function, absolute function is involved. Okay. as absolute function is involved, then our function become it become like difficult to get differentiation, or difficult to do differentiation on that function. Okay, to take derivatives. Okay, because it has in the case of absolute function, we it is not defined at every point. Okay, due to this issue, there is not multiple solvers in the case of Lasso by Sklearn, but in the case of Ridge, they have provided multiple solvers here. Okay, all the solvers we will not see here. Okay, but I have told you here they have provided all the solvers, multiple solvers. Now come back to our code, and again in the same way, like if I will show you our original polynomial regression function. Yeah, this one. Here, just I have replaced my linear regression by my Ridge regression. And here, instead of passing degree, here the alpha value will pass and it will come directly to here. Okay, and in that case, I will not use a sparse coefficient because it here maybe in the Ridge they have not provided as. Yeah, they also have not provided sparse coefficient. The reason is the same, that because in the ridge regression, there is no chance of making coefficients equal to zero. Okay, so there is not such coefficient that are uh, like equal to zero, and some sparse coefficient that are not equal to zero. All the coefficients will be not equal to zero, closer to zero we can say, but will not equal to zero. Now here I will show you ridge regression function that I have laid here. This one you can see here, ridge regression. Here I am using a ridge regression. Okay, and I have made it the solver class key. And if we will not use a class key, it's up to us. It by default it can use auto, and with respect to data, it can select by itself what should be the solver here. Okay, according to data, it can select here. Like this is auto. By default is auto solver, and auto choose the solver automatically based on the type of data that we are passing in the reach. Okay, I will remove that for now. Okay, now I will small bracket. Okay, I will run that function. Now you have seen in the case of polynomial without penalty, we have that type of complex function. Okay, when we will make it ridge regression and I am passing here alpha value 0, means I am trying to uh, use the same cost function without any penalty. But here you will get again some different, it will be a little bit complex, but different uh, different model here instead of that model. The reason is that because of different solvers they are using. Linear regression using different solver, ridge is here using different solver. If I will make here, let's say this one is rich one. Okay, if I will make here that I am interested in the solver of this one, if I will use this classic solver here, if I will use this one solver. Okay, now again you will not get the exactly the same result, because again I am telling you there are some uh, variations of the solvers that are actually using. Okay, there can be a variation of exact close, they are not using exact closed form solution. Linear regression is not using exact closed form solution, because I told you in the part of the session that they are using singular vector decomposition and pseudo inverse technique. Okay, okay, here. Okay. Now, if I will run that function, maybe it will become more complex as before we have, but it seems really same. But anyway, here we are again having a overfitting problem. Our model is complex, or catching a lot variation in the case of training data points, but very weird in the case of test data points. And practically, we can see here that the score on training data points is 94, 0.94, but on the test data point it's very less. And mean square error is very high on the test data points. When you will run that Ridge regression, let's say, okay, and again see these are the parameter coefficients, and all the coefficients are non-zero here. Now, in the same way, if you will use here 0.2 like we used in the case of Lasso, we have used 0.2. Now, alpha value is 0.2. Here you can see there is no coefficient here, it has made equal to 0. But in the case of Lasso, you have seen in the case of Lasso 0, Lasso 0.2. Yeah, in the case of 0.2, a lot of coefficients become equal to 0 here. But in the case of Ridge, it is not making here coefficient exactly equal to 0. Maybe making it some closer to 0, but not exactly equal to 0. And again, it has decreased that uh, uh, like it has increased your test score, but not uh, some you can say significant increase here. If you can see here, previously was raised it is in the form of minus, so raised the power 27 is more lesser value than here minus value in the form of raised to power 10 raised to power 70. So, okay, it has increased your score on test data point, but not here is a significant increase. And here it also made some smoothness on the uh, training data point. The model is smoother, but again weird on the case of test data points. Okay, like I told you, in our case, like here we are using, we are trying to make simple, or we are trying to make polynomial 200 polynomial model. Make We are trying to make them to make it simple. So here we need to make some coefficients equal to 0, but Rich cannot do that. So that's why it will not give you a good result. Even you will like here I have used 200 as alpha value, which is quite high. It can make your like here you can see your coefficients very small, like 0.00900, which is very close to 0, but it cannot make it work equal to 0. Here you can see, okay, here it tries to make equal to 0, but exactly not we will get here equal to 0. Okay, in the case of like here I have used very high alpha value, that I have penalized my cost function a lot here. Here you can see instead of increasing, it has also decreased my score on test train data points, and again not improving on the test data points, and we are falling in the underfitting. Model become more flatter here, more flatter because we have decreased a lot in the coefficients, and I told you coefficients are slopes. When you decrease the slopes, your model will have will have lesser sharp slopes. When you have higher values, your model will have sharp slopes. Here your model is becomes flatter. And again, this is in the case of L2 penalty, you are not getting good model on the test data points. Okay. Now you have seen in our case where we have implemented our both models, lasso regression and ridge regression. Lasso works better a lot. Okay, it has reduced the complexity of model by making a lot of parameters, lot of coefficients equal to 0, and it also have overcome the problem of the overfitting, but it cannot work here. But there are multiple applications where it can work, where we don't need to shrink our coefficients, we don't need to uh, eliminate our coefficients, we have to shrink our coefficients. Like from the lasso word, lasso can work in both ways: least absolute, shrinkage, and selection operator. Why it is selection operator? Selection operator is for the purpose uh, it make the coefficients equal to 0 for the less important features. Okay, sometimes it can also be used as a selection operator. Which features are more important? We can select by using lasso. again, and one another important that in the case of ridge and lasso regression, we should scale our data. Okay, in the case of like a linear models, or in the case of um, linear regression and such type of models, we usually normalize our data before feeding to model. But in the ridge and lasso, it is really important to do a scaling our, you can say, features, okay, before feeding to the model. So I hope this was a technical and more explanation of the last session, and a little bit about how we can implement ridge and lasso. I've explained you here, and I have explained you the practically I have shown you here that how lasso can make some coefficients equal to zero, but ridge cannot. Sometimes we have we need lasso, and sometimes we need ridge. Okay, and both usually used to penalize, or you can say to overcome the overfitting problem. So I hope you got a learn, and you got enough for the case of for the reach and lasso. In the later sessions, if we will come across in the case of classification, we will again can discuss that. And for now, thank you.